Before we start talking about tangents and secants, let's review the three kinds of segments within a circle that we should already be familiar with. The most basic of which is the radius, which is basically a distance between the center and a point on the circle. Another type of segment that we've talked about is a chord, which connects two distinct points on a circle. And a special type of chord that we've talked about is a diameter, which is basically a chord which passes through the center of the circle. With that in mind, we're going to define two other types of segments which are related to circles: tangents and secants. A tangent line to a circle is the line in a plane of that same circle that intersects it at one and only one point. An example of a tangent in the diagram that we have below would be line M. Line M is tangent to the circle because it touches it at one and only one point. A secant line is a line which intersects the circle at more than one point and passes through that circle. An example of that would be line P. Line P touches the circle at two different points. Now, if I call these points A and B, segment AB is a chord, but the reason we call line P a secant is it continues through that chord outside of the circle. So a chord which continues past and through a circle is called a secant line. In my second diagram, segment CA is a secant line because it's made up of a chord which continues on past the circle, while segment CE is a tangent because it touches the circle at only one point. So CE would be a tangent segment. So one question we might want to ask ourselves is, how many lines can be tangent to a circle? Well, let's investigate that. How many lines can be tangent to a circle at a given point? Let's look at a construction of this. Here I have a line segment which is tangent to my circle, and if I try to move that segment around, as soon as I change its slope, notice that I have a second point of intersection that this line is hitting my circle at. So since it's intersecting at more than one point, it's now a secant line. And if I drag this all the way around, it remains a secant line until I get back to my original position, and it becomes a tangent again. If I keep rotating this around, it is still a secant line until I get back to the original position of my line. So from this basic construction, we can see that there seems to be one and only one line which is tangent to a circle. So to sum that up, we have a postulate which tells us that at a given point on a circle, one and only one line can be drawn, which is tangent. Otherwise, if we move it around, it forms a secant. And there's a theorem which we could actually prove that if a line is perpendicular to the radius on a circle, then the line is tangent to that circle. And the converse is also true. If a line is tangent to a circle, then it must be perpendicular to the radius. So what that means is, in the context of my diagram, that if I know PS is a tangent line, so PS is tangent to circle O, then it must be true that line PS is perpendicular to the radius RO. So it must be true that these two segments are perpendicular to each other. So if I have a tangent, I know that they form right angles, or that they're perpendicular. Now, just like with chords in a circle, we looked at the angles formed by their intersection related to the arcs that they cut in that circle. We can do the same with tangents and secant lines. Well, taking a look at this diagram, does this relationship remind you of anything we've seen before? Note where its vertex is. The vertex of a line formed by a tangent and a chord is on the circle, just like it is for inscribed angles. So the relationship is actually going to be very similar. the measure of the angle formed by a tangent in the chord is half its intercepted arc, just like it was for inscribed angles. So looking at my tangent, my chord, if I was looking for the measure of angle DBC, DBC is this angle, it intercepts the arc from here around until it hits the other side of the angle, which actually occurs at its vertex. So angle DBC is going to be 1/2 of the measure of arc DEB. Similarly, if I wanted the measure of angle DBA, this angle, I can trace its arc and I find that the measure of angle DBA is 1/2 the measure of arc DB. Okay, so in the context of an example, if I know that the measure of arc AC is 72, well, arc AC here is 72 degrees, and I'm trying to find the measure of our angle BAC, this angle, well, the measure of angle BAC, since it's formed by a tangent and a chord, will be 1/2 the measure of its intercepted arc, which is arc AC. So that the measure of angle BAC is equal to 1/2 of 72, which is 36 degrees. Okay. Well, we can also look at angles which are formed by tangents and secants. Now, it turns out that angles formed by tangents and secants are 1/2 the difference of the two arcs which they intercept. Well, there are three situations that describe this theorem. The first is when I have two secant lines, which are lines that pass through the circle. They'll intercept arc AE, which is the larger of the two, and they'll intercept arc BD. So if I'm looking for the measure of angle C, the angle formed at the intersection of these two secants, that measure is equal to 1/2 the difference, or the difference of the two arcs divided by 2. So the larger of the two arcs is AE. So I'm going to take the measure of AE and subtract from that the measure of BD, and then divide that by 2. In my second situation, where I have a secant and a tangent, I'll again look at the larger of the two arcs, which is AD. So I'll have the measure of AD minus the measure of the inner one, which is from B to the next point that I intersect this angle, which is also D, so they share a point of intersection, the measure of BD, and divide that by 2. And in my last situation, where I have two tangents, I'll have my larger arc, which is ADC, the measure of ADC, minus the smaller of the two arcs, which is the minor arc AC, and divide that by 2. That will be the measure of my angle. Oh, I left my measure mark off over here. So those are the three possible situations. It's always the larger minus the smaller divided by 2 would give me the angle of intersection. So let's look at the examples for this. So an example where I have two secants, I tell you that the measure of arc AE, use a different color so that it stands out. The measure of arc AE is 150 degrees. The measure of BD is 70. So BD here is 70 degrees, and I'm looking for the measure of angle C. which is my angle here. Well, the measure of any angle is 1/2 the difference, so that'd be 150 minus 70 over 2. So 150 minus 70 is 80 over 2 would give me a 40-degree angle. So the measure of angle C, this angle, is 40 degrees. Another example, slightly trickier, is if I give you this situation. Now at first glance, it may seem like I didn't give you enough information. All I told you was the measure of our QR. Well, the measure of our QR is 120. I need the measure of arc QSR in order to figure out what the measure of angle P is. Well, notice how these two arcs are related when I highlight them. Together, these two arcs form a full circle, which should be 360 degrees. So if I wanted to know the measure of arc QSR, I could take the 360 degrees that's in the whole circle and subtract from that the measure of minor arc QR, which is 120 degrees. When I do that, I find that it's actually 240 degrees. So now I know the measure of that missing arc. So this situation actually turns up quite often when you have two tangents, because tangents only touch the circle at one point. When I have two tangents, they'll divide the circle into two arcs. Now, in order to solve the question and find the measure of angle P, the measure of angle P is equal to 1/2 the difference of the two arcs that I just found. So that would be 240 minus 120, which gives me 120 over 2, which is 60 degrees. There are several other examples in your packet, so I'd like you to go through that. Try each of those examples using these three relationships, and we'll go over any questions you have tomorrow.